Today we are very happy to have Dr. Andreas Baumgartner from CU. And Andreas received his PhD from the University of Canterbury, New Zealand, 2006. Work there was on radar measurement of mesosphere winds in the Antarctic region. And after that, he went back to Germany to work in Max Planck Institute for Chemistry as a postdoc. And then he served as a project manager in German Aerospace Center, DLR. And currently he's a research associate at CU Aerospace Engineering Department. And he's working on the Global Electric Circuit project, which is going to tell us more today.
Thanks very much, Henley. And thanks for the invitation to speak here. I will be talking about the exciting field of the global electric circuit, and that's a very diverse research field. I myself mostly work on the conductivity of the troposphere and stratosphere. And while HAO has several connections to the global electric circuit field, the stratosphere-troposphere conductivity is probably not the main aspect of HAO connections. So I thought I'd spend half of the time of this talk to talk about a little bit about the history and motivations for studying the global electric circuit. Then the second half, I'll talk about conductivity and how that translates into potentials and currents using GEC models for three different sort of scientific scenarios: a solar cycle influence on the global electric circuit, volcano influence, and the role of non-electrified clouds. But let me start with telling you what I'm not going to talk about. I'm not going to talk about the exciting stuff, the blue jets, red sprites, and elves. That's all stuff that happens on a very short time scale. And I'm going to talk about time scales that are longer than that, longer than about a second or so. Generally, the atmospheric electricity work is sort of divided into electromagnetics, AC field, and DC electrostatics. I'm only going to talk about DC. So this is a sort of very overview picture of the global electric circuit from a paper in Physics Today. The energy source for everything that's happening in here is basically solar heat that creates convective updraft and thunderstorms, and at the end provides positive charge sort of at the tropopause level and a negative charge mostly below. That's at least the sort of average case that's happening. And because of the potential differences, then you get currents flowing up to the ionosphere called Wilson currents. Got him a Nobel Prize for finding that out. And they then distribute around the rest of the globe. And because of the potential difference between the ionosphere and the ground, there's a small current going downwards. And that is slightly changed by different features of the atmosphere, so aerosols, clouds, for example. To give you a few numbers, there's sort of the same picture, just with numbers to what's happening. So with about 40 flashes or so per second, the thunderstorms overall generate 1 to 2,000 amperes that charge the ionosphere to about 250,000 volts. And that potential difference then drives this fair weather current in the region where there's no thunderstorms of about 2 to 3 picoamperes per square meter. The total resistance that goes through, so the total resistance of the entire atmosphere is about 200 ohms. You can also look at the system as two capacitor plates and say this is a capacitor with about 1 farad and a time constant of a few minutes. So if you would turn off all the thunderstorms, within a few minutes your ionospheric potential would be would disappear. So let's go back a few hundred years to this gentleman here, Benjamin Franklin. Although the discussion actually started in France. Apparently they didn't have anything else to do than to wonder what's going on with lightning and electricity in the atmosphere. There's a lot of people talking about that, and Benjamin Franklin got involved in that discussion and just suggested, well, let's put some conductive rods and try to catch some lightning with that. And then connect those rods to something called a Leyden jar that had just been developed. It's sort of a very early form of a capacitor. That's this thing over here. It's basically just the early form was just a glass of water or a bottle of water with a metal rod sticking out. And that's a very small capacitor. The French actually beat him to it. They performed the experiment in northern France, but they didn't manage to catch a lightning. So no one was killed. In June, Benjamin Franklin tried it himself. So he climbed up on top of the spire of the Christ Church in Philadelphia, and standing there in a lightning thunderstorm with a metal rod in his hand, he probably thought, well, this might not be a really good idea. And he didn't actually manage to get struck by lightning either, which is why he was still alive to perform the same experiment with a kite instead. And he didn't take anyone else to look at how he does the experiment apart from his son. And I suspect he actually made his son do it because he probably thought it's still pretty dangerous. But what he did was he built this kite and with several strings attached to it, and put a key on the string and connected that to one of these Leyden jars. And while he didn't catch a lightning with that either, the electric fields nearby were still large enough to have the strings go apart from each other, so there was an electric field between the strings. So he figured out that there was probably some electricity, or electric fire, what he called it, in the air, and then probably charging his Leyden jar. And being a good scientist, he actually published this and sent this to the Philosophical Transaction of the Royal Society. About a 2-page paper, and I just highlighted these 2 sentences here. The kite is to be raised when a thunder gust appears to be coming on, which is very frequent in this country. And then when the rain has wet the kite and twine, so that it can conduct the electric fire freely, you will find it will stream out plentifully from the key to approach of your knuckle. So apparently it worked. A few years later, Charles Coulomb did some experiments in his lab, and he wasn't actually trying to prove that the air is conductive, because generally people thought, well, it's only lightning strikes that can make electricity go through air in some form. He was actually rather annoyed because all his experiments didn't work out as well as he thought, and that was because the air is conductive. But still, he can be credited for finding out that even atmospheric air without any lightning is actually conductive. And I'll be talking about how conductive it is in the sort of sciencey part of the talk later on. And it was pretty quiet for a while. In 1859, the big next milestone happened. Lord Kelvin managed to measure the positive potential gradient of the air. And that was actually quite surprising that there was something happening at all, because people thought, well, when there's a thunderstorm, you have an electric field, but when there's nothing happening, then you shouldn't get any electric fields in the atmosphere. And it is also very tricky to measure that, because everything is much more conductive than air, including your instrument. So if you have any objects around, you're going to destroy your electric fields that you get, and this is one of Lord Kelvin's electrometers here. But he managed to perform that measurement and got a gradient of 137 volts per meter, which is actually really close to what it should be. So it's quite amazing, really. The ionosphere, or the highly conduction, or the high conductivity of the upper atmosphere, so it's sort of the discovery of the ionosphere, was then found in 1895 by these 3 gentlemen. In terms of lower atmosphere electricity, Hess and Bergwitz were the next two big names there, because they discovered that not only radon or radioactive decay in the lower atmosphere ionizes the lower atmosphere, but also cosmic rays ionize the atmosphere at higher altitudes. Unfortunately, the Nobel Prize only went to Hess, but Bergwitz was actually the first one who noticed that. He got his friends to, in the ballooning club to install an ionization measurement, and he just wanted to see how the ionization rate decays with height, because that's what people thought should be happening. But instead, he found a decay, but then an increase again. And then people thought, well, that must be his instrument, that is wrong. His colleague told him, don't you dare publish that, otherwise you'll ruin your academic career. He did, however, give the data to Hess, who then later on proved that this is actually true, and that must be due to some cosmic rays coming from outer space. This was a very exciting time for scientists. He actually got to fly on balloons for other types of measurements as well. This guy is Wiegand, who's measuring conductivity, the function of height here. And they did lots of flights in the sort of those 10 years here. But the big sort of next milestone was by E.T.R. Wilson, who put all the information that they had gotten by then together and showed that, or suggested that the continual atmospheric ionization from thunderstorms charges the upper atmosphere, and then that returns via a small vertical current density in regions where there are no thunderstorms. Got him a Nobel Prize for that suggestion. To further look at that and prove that this concept is true, scientists on the Carnegie vessel came up with the Carnegie curve through lots of measurements of the potential gradient during 10 years, or actually 20 years, and 500,000 kilometers that they traveled on sea with this boat here. It's actually made entirely from wood because, as I said, any objects, especially any metal objects that are conductive, will make your electricity measurements of all kinds very tricky. And one type of instrument they use here for measuring the potential gradient, and basically you just had an electrometer that you had to look at to see what the gradient is, and then you point your collector to different angles to measure the electric field in different directions. And what they found was that the electric field varied with one measurement to the next. But it didn't follow local time, what you might have expected, but it rather followed universal time. When you plot that, it looks like this. In the early morning hours, you have a very small potential gradient, and that increases towards the late afternoon, evening hours. This is another ship, the Maud, that made similar measurements. And that actually agrees with the concept of Wilson that it's thunderstorms that generate this potential difference. Because if you look at the area of land thunderstorms in the different regions, because the sun moves from one area of the globe to another during the UT, on a UT axis, you can see that the peaks correspond to the large areas where you have thunderstorms. So Africa and Europe, which have thunderstorms mostly sort of in the late or in the afternoon here, create the peaks here. And when the sun is over the Pacific, not much is happening. So after that, people didn't actually measure much of the electric circuit, but they modified it. Atmospheric nuclear testing in the 50s and 60s created a huge burden of radioactive material in the stratosphere. And the upper curve is potential measurements. And in those years here, you can see that the potential increased from 250 to almost 350 kilowatts. So it made a huge impact on the global electric circuit. The next interesting thing was measurement of the conductivity profiles in a big workshop with lots of balloons and lots of instruments. And I'll be showing some slides of that later on for verifying our own conductivity calculations. That was just happening around the corner in Wyoming. And just a year later, NCAR's Ray Roble and his colleague Hayes presented a first analytical solution to the GEC problem to calculate currents and potential from a given conductivity distribution and source distribution. And they used spherical coordinates and the Green's functions to do that. That's just a plot from their first paper here, showing the potential distribution as a function of latitude and longitude for 25 kilometers. And you can see, of course, the thunderstorm regions here and leave an impact even at 25 kilometers. Again, back to conductivity, the first 3D model of that was presented in 2006 by Tinsley and Zhu. And slightly different solution to calculate potentials and currents was presented by Odzimek and Rycroft in 2007. And that brings us to the present. And this is what's happening at present. Jeff Forbes, the PI of a big project, NSF Frontiers in Earth System Dynamics, with the title Electrical Connections and Consequences Within the Earth System. And that's where my paycheck comes from. CU, NCAR, and Pennsylvania State are involved with that, with different parts on that. If you want to know more, there's a website here that if you Google that, you'll find that relatively easily. So why did the NSF fund this project? What are the motivations for studying 2 picoamperes per square meter? And for me personally, the diversity of the aspects that you get in this research field is very fascinating. It combines atmospheric physics, chemistry, solar terrestrial physics, and Spark must have found that fascinating as well. There's actually a 10-minute video just from last year featuring Jeff Forbes as a cartoon character. If you want to see that, just if you Google atmospheric electricity and Spark, you'll find that on YouTube. That's very good. I can highly recommend to watch that if you have 10 spare minutes sometime. Also, you can use the global electric circuit for sort of as a natural framework for investigating global change. I already showed you that nuclear testing had a huge impact on ionospheric potential, but pretty much any variable of weather and climate, be it aerosols, galactic cosmic ray, influx, changes properties of the global electric circuit. And you could potentially detect that through measurements of the GEC. Now the big question is, with 3 question marks, if this process works in the other direction as well. So if we have changes on the global electric circuit, for example, the electric field strength, does that change in any way the weather or climate? For example, through cloud condensation. The peak of that discussion was probably somewhere around 1997 when 2 people from Denmark, Svensmark and Friis Christensen, published this figure here. It shows the cosmic ray intensity, which is the thin line here, and satellite cloud cover from measurements of oceans only. That's the solid line here. And of course, the agreement between those 2 is very stunning. And so that caused a huge discussion on if there are any feedbacks. And that went on for the last 15 years, and it's probably haven't reached the end of that. Just citing from a paper from last year, which used the Terra satellite, which measures albedo, and found no statistical significant correlation between cosmic rays and global albedo or globally average cloud height. It also found no evidence for any regional or lagged correlation. Also, an approx superposition analysis of Forbush decreases reveals no detectable albedo response to cosmic ray decreases. So the fight is going on. The idea behind all that, although we're only looking at correlations at this stage, is that probably cloud formation processes that might be influenced by ions. If you throw in some buzzwords like electroscavenging, you can come up with some mechanisms that E-fields or ionization rates change your cloud formation processes. I'm not going to go into the details of that, but there's a big experiment at CERN going on trying to use a pion ray to see how you can change properties of cloud formation. Another suggestion, really just based on correlations as well, of how you create a feedback, or a feedback that you might get is, was suggested by Mansourov in 1974. And what they looked at was the interplanetary magnetic field BY component, the ground level pressure poleward of 80 south. And that was revisited by two papers in 2007 and 2008. And while this one looks very messy, they did find correlation coefficient of 0.9 with new data from 10 years. This is the BY component, and this is the surface pressure component. However, really just based on correlation analysis, and what does that really tell you? So I think we do have two large gaps in our understanding here. We've got a basic conceptual understanding of the global electric circuit. And what people have done is use correlations to show or to suggest that we might have some climate effects through that. What we don't have is any GEC models that give you the electric fields, or any understanding of how these then would change your, for example, cloud formation processes. So we have no way at the moment to rigorously investigate if any of those claims are true or not. So this part is sort of what we're trying to address in this NSF project. And it doesn't really look that complicated if you just look at what you need to do. All you need to do is solve this Poisson equation. And that'll give you the potentials and current densities throughout the global electric circuit. What you need to do for that is to calculate or measure your charges and current sources. So that's your thunderstorms. And you need to know the conductivity as a 3D variable of the global electric circuit. And unfortunately, conductivity is influenced by a lot of different things, so it's not that easy to get those numbers. Of course, galactic cosmic rays ionize the atmosphere, and sometimes when the sun smiles, you also get solar energetic particles that contribute to ionization. And at the surface, radioactive decay of uranium and thorium in the ground contribute to ionization mostly through radon. How do we get rid of those ions? Most simply just by ion-ion recombination. However, that's also a function of temperature and pressure or number density in the atmosphere. And also through aerosols and clouds, because ions like to attach to larger particles like aerosols. And then they basically reduce conductivity because they're too large and their mobility is too small. Then what you need to do is you multiply the ion concentration times ion mobility, is also a function of temperature and pressure, times the constant electron charge, and that gives you conductivity. Now you need a lot of things to know a lot of things about the state of the atmosphere: temperature, pressure, aerosol concentration, clouds, and the easiest way to get all that information is in a model. And Wacom provides most of these things, and so it's relatively easy to calculate conductivity just inside a model, which will give you a very good first estimate of that. Because measuring conductivity as a 3D variable is not really possible, because it's not a number that you can get from a satellite measurement. So this is the ionization rate calculated in Wacom, and just shows you the different altitude regimes of the ionization sources. Galactic cosmic ray give you a maximum at 10 to 15, 20 kilometers. So that gives you about up to 40 ions per cubic centimeter and second. In the lower atmosphere, it's radon, and the color ranges sort of give you the variability over latitude and time. So galactic cosmic rays have a huge variability in this region, and radon is anywhere from 0 over the ocean up to maybe 20 ions right at the surface. Of course, when you've got a solar proton event, you can reach ionization rates of up to 10,000 ions per cubic centimeter and second, or even larger numbers. This is just 2 examples of 2 solar proton events. Their altitude also depends on the charge of those particles. And this is what we get for conductivity. This is conductivity as a on a log scale and as a function of altitude. And you can see it decreases exponentially, or increases exponentially, mostly. And the variability just from galactic cosmic ray and temperature variability is not that huge, although, of course, we're on a log scale here. But what really makes an impact is aerosols and clouds. They can really reduce conductivity by up to 2 orders of magnitude locally if you have substantial amounts of those in the troposphere. If you look at that on a map, you have to integrate 1 over conductivity to get the total resistance of 1 atmospheric column. So you can really think about that as just a resistor sitting between the ionosphere and the ground for every spot on the surface. And you can actually see a lot of things just from looking at a map like that. For example, when you're high up on a mountain, your resistance is not as high anymore because just the distance between you and the ionosphere is not as large anymore. You can also see that the galactic cosmic rays leave an imprint. The minimum of galactic cosmic rays leads to a maximum in the resistance because there's less ions to ionize your atmosphere. So that follows the galactic cosmic ray minimum. You can also see these very large resistances here, which are a result of aerosol, for example, here from biomass burning, probably. If I leave out the continents on this slide, you can still see them, and that's because radon is only emitted from land surfaces, and that gives you a very distinct order between ocean and lands. We also include clouds in that calculation. The picture looks a lot messier, just because clouds have such a huge influence. You can all that you can see is clouds in this version. So here, for example, big cloudy areas of the planet. As I said, there's not very many measurements of conductivity, and the only way really to get a profile is to sample it with a balloon, or sample it with an aircraft at a specific altitude. And that's the background plots in this figure here are from a NASA ER2 aircraft measurement at 20-kilometer altitude. And the range between the 2 red lines is what the model predicted for that location. And you can see the agreement is pretty good. Not much we can improve here. And this is a slide from 1982 from this workshop in Wyoming where they launched lots of conductivity probes. And you can see again the exponential increase with altitude between the different instruments here. And the red line I just added model. And it lies between those measurements. So again, I think that's a very good agreement. So moving on to the science a bit, what does the solar cycle have, or what role does the solar cycle have for conductivity and also for ionospheric potential and other numbers in the GEC? For that, of course, we need a bigger version of model that not only conductivity, and what we also need, of course, is galactic cosmic ray varying with solar cycle. And we got that from a NASA project by Chris Mertens. It's actually had a different purpose, but it's very useful for calculating galactic cosmic ray ionization rates. It's called NIRAS, and you can just use that as an input for the conductivity calculations. What we also need is current sources, and they come from the TRIM satellite, and then we combine all these things. So need to solve the Poisson equation, and that part of the model is done by a group also from NCAR at CISL by Natasha Flyer and Victor Bayona mostly. And they use radial basis function generated finite differences to solve that problem. And that gives you currents and potentials at the end, which is what I'll show you in a second. But again, back to conductivity for a moment. These are conductivity changes with respect to the long-term mean as a function of altitude and latitude. And you can see that not only the most of the galactic cosmic rays end up at the poles, the variability is also largest at the poles. And the variability is up to 45% or so of the ionization rate variability here at 15 kilometers or so at both the north and south poles. And this is for the last solar minimum, so that's where we have the largest conductivity increases. And this one is for the solar minimum before that. So you can see the last solar minimum is of course also a galactic cosmic ray maximum. And that as a function of time here, again, the blue line is the resistance. Now as a function for the last 5 decades, you can see nicely the different solar maxima. And for the resistance, there's also a minimum here where we have a conductivity maximum. The other two lines, the current and potential, are then derived from this big model environment then. And the total current doesn't really vary that much, mostly between 1 and 1.1 kiloamps. But the potential shows a big variation, which is in phase with the resistance variation. So it varies from 250 to about 320 kilowatts. And why is that? Now, we saw that the conductivity changes mostly at higher latitudes. And you change this resistance here in the fair weather region, so you don't change anything in the area of the thunderstorms, which is mostly at the equator, of course. Then potential is really just the amount of current times the fair weather resistance, because it's a voltage drop over your fair weather resistance. We saw that the current is not changing very much. And then a decrease in resistance in the fair weather resistance will lead to a potential decrease. So that's why these two curves here are in phase. It gets a little more tricky when we look at volcanic eruptions. Volcanic eruptions, of course, cause a lot of aerosols in the stratosphere, and that leads to lots of conductivity changes, but not only at high latitudes now. This is sort of the most extreme case that you can think of, 100 times Pinatubo eruption, which is maybe roughly what the Toba eruption 100,000 years ago was like. And the aerosol data I actually got from a few colleagues, Jason English and Ryan Neely, who did simulations also with Wacom to look at the aerosol burden. And you can see that after the eruption here at 0, this lasts for several years. Be a slow decrease of stratospheric or whole atmospheric aerosol burden. And the conductivity that you get from that. And You can see the decrease here. So this is only showing the showing conductivity at a specific altitude at 14 kilometers. So you can see here the large reductions which happen right after the eruption, but they only last for much less than 1 year. Which, is mainly due to the fact that conductivity depends on the number densities. And what happens after the eruption is that you get coagulation of smaller particles, which leads to heavier particles, which leaves your total mass or burden in the atmosphere similar, but it really reduces your number density, which is why the effects don't last very long for conductivity. However, in the few months after the eruption, they are huge. This is the percentage change in conductivity between before and after the eruption, and you can see that you basically lose all your conductivity. So it's a huge resistor. It's a conductivity hole. You reduce your conductivity by 99.95%, so not much left. So what does that do to the currents and potentials? The first one here is resistance for 3 different eruptions: Pinatubo, 10 times Pinatubo, and 100 times Pinatubo. And you increase your total resistance from 200 to about 300 ohms for the largest case. For current, reduce your current, and that's just scaled by the size of the eruption. More complicated for the potential. Even for the largest eruption here, you can see that the potential increases rather than decreases compared to the Pinatubo, one-time Pinatubo eruption. So that seems more complicated. And the reason for that is we're not only changing the fair weather resistance, we're also changing the resistance above our thunderstorms. And when we do that, the current is not fixed anymore. So the potential change will depend on current and fair weather resistance changes. And I've tried to indicate that here. So we increase our volcanic aerosols, increase our resistance. If we increase the fair weather resistance, we increase our potential. It's just the same as with the solar cycle variations that we looked at before. But we also increase the resistance above the thunderstorm, leading to a current reduction, because then more current is sort of shortcutting around the thunderstorm, and not as much as reaching the ionosphere anymore. So that leads to a decrease in potential. So it really depends on where exactly the aerosol is and the weighting between those, see what potential variation we get in the end. If we also change the actual thunderstorm region resistance, we don't actually know what's going to happen to current and potential, because then microphysics is going to be involved, and we haven't really got an understanding of how that changes a thunderstorm in its properties. A short look at a solar proton event. That's the one from the 20th of January 2005. On the left, I'm showing ionization rates. And because we really wanted high resolution and high time resolution ionization rates, I used the IMOS database for that. And of course, this is the Antarctica here in the background. And you can see ionization rates up to 2,000 ions per cubic centimeter in second. This is at 30 kilometers. And you can also see these 2 dots here, these 2 black dots. And luckily, during that time, there was a balloon flight measuring conductivity. And well, that's of course really cool, because you can see what happens during a solar proton event. Unfortunately, it was very much at the edge of the increased ionization region here. So if you look at this, at their measurements, which are the black line here, this is before the event, and then you get the solar protons coming in, increasing your conductivity, and then slowly decreasing over time. and the Wacom model results with huge error bars because we're in this really sensitive region here at the edge. Shows, in principle, the same thing is happening, but it would have really been easier if the balloon would have been flying here rather than here. I'm sorry? I think this is averaged over an entire day, to be honest. So, yeah. Depend on time of day. I can't show you any electric field changes from that because, of course, the ionosphere will do different things during that time as well because the magnetosphere will react to the solar proton event. So that will be the final stage of the whole model system when we have when we can combine knowledge of that into as a boundary condition for the Poisson equation. Calculate what the electric field changes from that will be. So that's work in progress. Have not really that much. Let me skip that. We'll have some time for discussion. I hope I was able to show you that the global electric circuit is a very diverse field in atmospheric science with many aspects from classical meteorology to solar terrestrial physics. We have now a very good handle on conductivity by using Wacom. So sort of an initial state, an initial phase of 3D model to derive currents and potentials from that. Volcanoes increase resistance dramatically and change total current and ionospheric potential, but the sign and magnitude of the potential change will very much depend on where your aerosols are. For the solar cycle, the current is constant, but potential varies by up to 20%. And I didn't talk about the clouds. That's it. Thanks very much for your attention.
Questions for Andreas? That's a quick question. So did they observe any significant changes in ionosphere during the should be some changes, right? Yeah.
We had enough measurements, then that question would be easier to answer. At the moment, there are only sort of one measurement a year or so. That one. These individual points here are only individual measurements of, and if you look at the 1991 eruption, since the effect only lasts for a few months anyway, it'll probably be black magic to read something from those points. But we'll try in the future to see if that makes any sense.
Wacom model, do you differentiate between the different types of cloud when you do the calculation of the activity?
Different types of clouds in the sense that we're distinguishing their altitude. And, the CAM part of Wacom gives you, for every model layer as a function of altitude, a cloud fraction. And that can be used for the conductivity calculation. What we don't know is how much, or what type of cloud it is in the sense of how much does each individual cloud drop conductivity. Is it a factor of 1/50 or 1/10? That will certainly vary with different types of clouds. Cirrus cloud will be different to a stratus cloud. So that'll be future work.
On that slide 27 or So 28.
On the solar cycle one? 28.
Yes, this one. Yeah, it looks like the resistance is lagging the changes. The potential changes occur first.
Interesting. Physically, of course, that's not really possible, but maybe that has something to do with the current changes that we're also getting here. Because here we're on the, for example, if we look at this case here, the current drops, which would mean your potential drop, but at the same time, resistance does something else. So it might be, again, a small contribution of what's happening with the resistance in the region where your thunderstorms are. And maybe galactic cosmic rays don't have a slightly different phase in their variation as a function of geomagnetic latitude. Just a first guess. Interesting observation, though. Thanks.
Gauss' turn. Next, we got Gang. Next is you.
Okay. Can you tell us a bit about, you showed ionization rate from a cosmic ray, and I'm wondering what kind of...
There are two sort of versions that are used for galactic cosmic rays. There's a very simple parameterization just depending on geomagnetic latitude and time. Sort of solar cycle goes in as a factor between -1 and 1. That was developed by Lee and others just using ionization rate measurements. For this work here, the NIRAS model is actually a really complex tool, but its main input database is neutron monitor counts. And then, I don't know what parts that model has. There's a 70-page paper just appeared in space, JGR space, so it doesn't seem to be that simple, but Chris Mertens might be able to tell you more about that. And Mike Wildberger worked with him a little bit on that, so if you...
This is probably a follow-on question and probably addresses it. So primary input is the galactic cosmic rays, and a secondary input, that box?
In this one here? It'll be in there. The problem is, at this stage, we're using monthly means. So any short-term sort of particle events will be smeared out completely. So this is really just following galactic cosmic ray or neutron monitor data.
You're also putting a magnetic input into that model? That was where I was going with that. Thanks.
And in principle, that data is available in really high time resolution since it's used for flight, aircraft flight dosimetry. Yeah, at this stage, we're doing monthly averages. Yeah.
Do relativistic particles from the radiation belts precipitating down into the atmosphere have any appreciable influence on the conductivity profiles. I know the X-ray Bremsstrahlung from them is observable at balloon heights, because that's exactly what the barrel mission is measuring. So could there be coupling between the radiation belt dynamics and this global electric circuit as well?
In principle, yes. And again, some very brave scientists have come up with correlations between Bremsstrahlung events and temperature changes over Boulder.
Calculations for the relative importance of cosmic rays versus precipitation radiation belt particles. Are they comparable? Is one orders of magnitude larger than the other?
Main altitude range that you get rid of the Bremsstrahlung actually is deposited where you would see it. I'm not even sure about that at the moment. Is that in the mesosphere somewhere? I suspect it's higher up. But there have been suggestions that it has some importance, so it's certainly not the end of the story.
I was wondering if there's a volcano eruption, will that block some of the cosmic rays?
Sorry, say again?
Volcano event, will that block some of the cosmic rays?
Oh, good question. Yes, it should. Definitely not taken into account, but it would modify your energy loss because your number density is not changing that much. So, I mean, if you have large particles, there'll be the mass changes a lot, but your actual number density probably doesn't. So, on that hand, it might not. Yeah.
Not anyway.
I haven't read anything about that. Yeah.
No more questions. Let's thank Andreas again.